Okay, hello everyone. Welcome back to another DDLC seminar. Today it is our great honor to have Professor Mark Campbell. Professor Mark Campbell is a professor in mechanical and aerospace engineering at Cornell University. He earned his bachelor degree from CMU, Carnegie Mellon University, and his MS and PhD from MIT. His research interests focus on control, autonomy for robotics, aircraft, and spacecraft. His research areas include machine learning, perception and sensor fusion, optimization and learning-based control and planning, decentralized distributed estimation and control across teams, and human-robotic interaction. He has received multiple university and national teaching excellence awards, including Cornell's Stephen Vice Presidential Fellow Award, Ralph Watts Award, Douglas Whitney Award, and many others. He has served as an associate editor for the Journal of Guidance, Control and Dynamics and the IEEE Transactions on Aerospace and Electronic Systems. He has also served as an associate director on the American Automatic Control Council Board of Directors. Professor Mark Campbell, welcome.
Thank you very much. Appreciate it. I appreciate the invitation, Andres and Panos, in setting things up. So I'm going to talk a little bit about some work that my group has been doing over the past few years, focusing on uncertainties in deep learning. I sort of listed some people that we've been collaborating with, a couple of CS professors here, Kilian Weinberg and Bharat Hariharan, and Harry Chow, who's was a postdoc with us, but is now at Ohio State. And then just a whole host of students that have really done a lot of this work. So just to kind of set the stage, if you think about deep learning tasks, and I'm focusing a little bit more on the perception side of things. So, but if you focus on the deep learning task for robotics, self-driving cars, this is just an image actually from our car. And there's a bunch of different things that are happening here that deep learning or machine learning or deep learning can help out with this, okay? So there's the traditional thing, which would be just detections, right? So this would just be the boxes around each of the objects, or it could be around the different pixels and things like that, right? So you do detection, there could be tracking, so that's basically locating this person over time. Classification, which would be the type of object, of course. And then there's forecasting, which is predicting into the future. But then there's some other things you could potentially do. For instance, especially here in Ithaca, New York, you have a lot of snow-covered roads and those types of things. And so understanding where the road is, even when it's snow-covered, is an important challenge. And so there's a lot of interesting areas to be able to use deep learning. And so again, that's just a little bit on the perception side of things. There's one other one other task that I'm going to explain because I'm going to use it as a case study here, and that's visual localization. So that's the example on the right-hand side here. And what happens is if you basically have a set of images that are also geotagged, and you're driving along and you basically want to locate where you are based on image matching and then basically pull out the geotag as your location. So I'm going to kind of use that as a case study because of some of the data that we've actually collected. Okay, so those are just a few examples of the task, but of course there's a lot of errors that can actually come up. So this is an image when we were actually just running some 3D detectors on a single image, trying to put basically boxes around each of the objects. And so if you look at the bottom image, this is actually what it actually looks like, and it's a little hard to tell exactly what's going on. If you put it into bird's eye view, it basically, this is from the top. I've actually also overlaid some LiDAR information so you can actually see what's happening. So the truths are the green boxes, and so there's a couple things you want to see here. Is that in the left side here you have some missed detection, so basically some missed boxes. You also have some partial detections. You only are kind of seeing the front of the cars and things like that, right? This object right in the front here is also a missed detection, so we're only getting sort of the corner of it. We probably got it when we were driving along, so if you're tracking, that helps with that. But then in the far right up here, we have an incorrect detection. So it's actually all the way back up in here. So it basically detects an object that's actually off in the grass of the car, or grass of the area. So anyways, this just gives me an example of some of the mistakes that it actually makes. If you work in the area of model-based estimation, which is a lot of what my group does, these are all fine. You can handle all of these, but you typically need to know a model of what these are. So I need to know how often am I going to miss a detection? How often am I going to make an incorrect detection? And so having some parametric or probabilistic model of those is really kind of key. So this is just an example in terms of just the detection and tracking problem and things like that. But there's other kinds of problems that come up with deep learning. So this is an example right here of Tesla looking out on the horizon and it actually thinks the moon is actually a yellow light. So that's actually a pretty big mistake. And there's a host of other examples like this that you can actually see on the internet. So these are some mistakes in deep learning. And so one of the goals that we wanted to do, and we've been trying to work on for the past, I would say 3 or 4 years, is trying to quantify these such that we can use these as in our estimator and trying to build up our belief network. Okay, so how can we predict and quantify these errors in deep learning? That's basically what the goal is, and that's kind of what I'm going to focus on in this talk. So what I'm going to do is I'm going to kind of do a couple of different things. The first is I'm going to introduce the Ithaca 365 dataset. This is a dataset that we collected, or really my students collected. It sort of started over COVID, and we were able to label some of the data and publish it as CVPR. So I'll talk a little bit about that and how we used it and some of the research that came out of it just briefly. And then I'm going to dive into this visual localization case study that I mentioned. And the data set is very special in that we drove the same route around Ithaca basically a couple hundred times. The data set only has 80, but we had a couple hundred versions of that. It's about 15-kilometer route. And so then we could see it at all different kinds of conditions: night, day, snowy, those types of things. And we can take advantage of those, the fact that it was repeated traversals in our research. Okay. And then finally, I'm just going to show some videos of some data that we collected in Hanoi, which is, of course, just an entirely different animal in itself. Okay, so first I'll go into Ithaca 365 data set. Okay, so I already kind of mentioned this right here. This is, if you're familiar with Ithaca, you kind of understand this. This is our car here. We hand drove the car. On top of that, we have different kinds of LiDAR. We basically have some 4-scan LiDAR, but we also have some high-density LiDAR, some Alster's OS2, so 128 scan. We have some a handful of typically 4 cameras that are sticking out the front, but we can put some sort of all around the car if we want to be able to do that. We have an NVIDIA DrivePX system that basically synchronizes all the data and collects the data with high precision GPS IMU data and those types of things. So we basically have a bunch of sensors. It's basically a big sensory car. And this is the route that we took. And so right down in here where, if you can see my pointer, that's our starting point, which is really close to College Town. It's basically near the building that I'm at right now. And that's where we house the car. So we basically would drive out. And then we kind of drive through College Town down here. If you're familiar with that, we drive downtown. Okay, so we have a little bit of town areas as we go through here. So we have traffic lights, some 2-lane one-way roads and things like that. We kind of do a loop going through here. Same kind of territory in terms of the scene. And then finally, right around in here, we actually get on a 4-lane highway. So this whole route out here is the 4-lane highway. You see, this is a little bit sparse in here because we wanted to sort of make sure that we have roughly the equivalent number of, for each type of scene, we have the equivalent number of images and things like that. Right at the top here, we get off the road and we basically drive through suburbia. So this is basically just some 2-lane roads, stop signs, driving by houses, but driving through, tree-covered areas and those types of things. And finally, come all the way down here and we go through campus again. And this is basically the place that you would actually see a lot of students, for instance. There would be a lot of stop-starts and those types of things. So this is our 15-kilometer route, and we drove this again hundreds of times. So I can pick any image like this one or any location, I'm sorry, right here. And what I can do is I can give you 80 images of what that looks like. This is what it looks like in snowy conditions. This is what it looks like, after a snow, but it's kind of cloudy and things like that. These right-hand sides are snow-covered roads, as you can kind of see, and these are some snowy conditions as well. So there's different kind of conditions that I can give you, at nighttime, all those kinds of things. So we can take advantage of that as we go through. Okay, so one of the things we did with this is we labeled the data set. We really wanted to focus on amodal data. So I'll explain what that is if you haven't heard the term. Amodal data basically means, I think what people in this area know what labeled data means. It basically means I'm going to take, let's say, a car and I'm going to either put a box around it or I'm going to draw around the pixels. What amodal data is I'm going to do that, but I'm also going to complete the shape such that if I look at, let's say, this pixel right in here, this is actually 2 cars. That actual pixel has two cars, right? If I look at this one at the front of this car, this is the car and also the location of the road. Same thing is actually open here. This person right here is a person, but also behind the person is the truck that they're actually standing on, right? And so if you actually take the labels and look at them on the right-hand side, you can see the overlap. And so that overlap is very important, especially if you're trying to deal with occlusions and really high density areas, which is certainly one of the areas that we're one of the research areas we're particularly interested in. Okay, so this is just an example of some of the labels that we have. So this is some of the 3D object labels. On the left-hand side, these are just some of the boxes. And then the amodal instance labels, which are basically the overlaps, those are some examples that we have right in there. So we did at least a handful of these in all kinds of conditions. So we actually have a labeled data set. So we can look at detection and tracking, sort of all the traditional metrics as we go through. And we also wanted to look at the road itself, and the road itself is important. This is sort of us driving on the 4-lane highway. The road is important, especially again in snow-covered areas like this. So the question is, would you be able to understand if it is snow-covered, what it actually looks like as you're going through? Okay, this is actually coming on North Campus and things like that. Okay. Okay, so just a little bit of a summary. I've talked about this already. 15 kilometers was the route. I say 40 traversals. Maybe that's what we actually put in the paper itself. I think the website has 80, and then we actually have a couple hundred on our server. So we have some of that for internal use and things like that. You can see the average frames for traversal, so basically about 17,000. And each frame has LiDAR vision, again, GPS, high precision GPS and things like that. There's different kinds of conditions, nights, rainy and snowy. So if I look at the bottom images here, this is the LiDAR feed under 4 different kinds of conditions as you're sort of driving along. And unfortunately, all these aren't running. I don't know why that is the case. Yeah, it sort of seems like the sunny and the night are stopping. I'm not 100% sure. But that's sort of the LiDAR case. And, I've already shown you sort of some of the images that actually come from there. Okay. All right. So that gives you an example, just sort of a summary of the Ithaca 365. We've done a number of different research directions for this because at least at the time it was pretty unique. Now there's a couple of more data sets coming out that has snowy conditions and things like that, especially over in Europe. But for a while, all the data sets were coming out of California and Europe, and they were all focused on very nice conditions, sunny conditions and dry conditions and things like that. So one of the big things we worked on, and this was really driven by a couple students with Killian and Barath, was looking at trying to do 3D detection with vision. Okay, so this is at the time, you can sort of see the papers up in the right-hand corner, 2019, 2020. We sort of discovered something unique, and that is that when you're trying, if I look at this image at the top, 3D detections is I'm trying to take either a single image and doing with depth or with a depth detector or stereo, and I'm trying to find 3D boxes of objects, right? So what we found, it was just very, very sensitive, and that was sensitive because when you're looking at it from the image in the image plane, if I would make a mistake, like on a pixel right here, it was a big mistake. It could be basically 100 meters away or even further. You might not be able to see how far away the error is. So that sensitivity created big problems in the deep learning detector. So one of the things we did, which is actually fairly simple, is we took a depth estimate from another network with the image, and we put them together to create basically pseudo LiDAR. And this is basically LiDAR that is generated with either stereo vision or monocular vision with a depth estimate and things like that. And what that did is now you're basically looking down, and you have a lot of pixels. You have a lot of pixels creating a lot of points, and you can actually then use all the LiDAR-based detectors as you can do that. And so there was just you can sort of see an example right here. When we started doing that, there was just a huge jump in performance. So this just shows some pictures here on easy, medium, and hard, and they're all about the same. But basically, before we actually did this in terms of stereo imaging, you're at sort of at 24%, whereas LiDAR based was 90%. But if you just do this trick, it basically jumped to 73. and then, or at least doubled, I would say, in each of these. And then we basically got incrementally better. Didn't quite get to LiDAR. Because LiDAR is just such a good range sensor, but it really did a really pretty good job. And really this, in my opinion, sort of transformed the community. If there's some of the Tesla AI videos talked about doing pseudo LiDAR in terms of using their vision systems and things like that. So it was an important step as we went through this. A couple other research things that we worked on, translating snowy night conditions to sunny conditions. And so this actually shows a video of what we're doing. So it sounds a little strange, but we sort of, think of it as always sunny in Ithaca. Basically, the left-hand image is basically during snowy conditions, and on the right is basically transform into sunny conditions, where it's a little bit easier to do detections and those types of things. So there's some nighttime versions of this and those types of things. And so for the most part, if you looked at detection and tracking and all this forecasting and things like that, it all got better by doing this, even though on the right-hand side, you kind of look at it and it's kind of grainy and things like that. But again, this is just a couple years ago, but it actually does a really pretty good job in terms of translating the images into sunny conditions and then running detectors on those sunny conditions. It does a much better job in terms of working with snowy conditions. This was some work actually from one of Killian's students that we were working on repeated traversals. So the idea here is that many times when you drive your car, you're going to work and coming back, or you're going to the market and coming back, and so you drive the same route. And so the question is, can you improve whatever tasks you're working on based on that? And so this actually showed that you can actually just develop a detector by those actually repeated traversals and things like that. So it just iterative self-training on its own to do 3D object detection, which actually was really pretty amazing in terms of how quickly it actually converged. You can, because of the A-modal data, we can actually then, some of the work that we actually ended up doing was doing joint shape and pose estimation. And so if you have, let's say, just a partial LiDAR scan of the front of the car, or you can only see the corner of the car, or, if I look at this occluded van over here on the left-hand side, you can actually put it through a network and as long as you sort of know, typically, as long as it learns basically what the typical shapes of cars are, you can actually complete it. And so the example looks like over here on the right-hand side where, I just had sort of the front LiDAR scans, but basically now I have a very big point cloud. And I can then use that for driving and understanding my locations and those types of things. And so this is really taking advantage of that A-modal data that I actually talked about. We did a lot of work on then learning about occluding models and figuring out how to reason about them and how to improve upon them. And so, this is an example here of if you have some type of initial point cloud, which you then put in bird's eye view, which is BEV, if you haven't heard of that. But basically, you can see if the car is over here on the left and you look all the way into the front here, as you go further out, you have fewer scans and you have some sparseness on the left and right-hand side because you can't see sort of what's going on because of occlusions. But just like you and I as drivers, we typically will know, okay, I have a car and I have another car probably behind it. There's a little bit of space in between. There could be a pedestrian walking in between. We sort of know all of these things. And that's what in-painting does. You can basically learn and reason about those spaces that are actually in between the cars and things like that. So you can generate different obstacles and then navigate in that space and things like that. So we showed that using this, not just basically doing this in painting problem, but basically using this for navigating, actually, what you're able to navigate 5 times faster is just in terms of a general start to goal navigation task. And then we've been working a little bit on forecasting. So early on in 2014, we actually did some work using machine learning techniques. These are Gaussian process models. And we had a couple of nice tricks where we actually embedded a closed loop physics-based model into the forecasting. So forecasting is basically predicting how cars in the environment are going to move at any into the future. So the example shown here in open loop here, I have some tracking uncertainty, and this is the location. You want to think of that. That's the initial location, and this is a prediction out to 20 time steps where we think it's going to go. So you can see it's actually turning left, but these uncertainty models are growing to be bigger than the lane, which doesn't really make a lot of sense. This is because it's an open loop open loop model, whether that's physics or not. But if you close the loop and actually use physics, you actually get models that look like this. And so it stays in the lane, it elongates because typically people drive the intersection at different speeds and those types of things. So it kind of does a nice job of that, right? So more recently, we've actually embedded that into deep learning, and we basically get the same thing. So the baseline looks exactly like what I had in the lower right here, the lower left here, which is the open loop. So it grows over time, and then the closed loop physics basically kind of keeps it pretty tight in terms of the uncertainty. And you're actually, one of the interesting things about the baseline models is it's just doing wacky things. So if you look at the green, this one right in here, it looks kind of smooth. But if you look at the steering here, it's basically going back and forth between, some of the maximum, it's basically turning left, turning right, but it's really, really quickly being able to do that. So it's a little weird in terms of how it's doing it. And it's mainly because it just doesn't really understand that, really your steering should be smooth and those types of things. One of the last things I'll talk about before I move on to the visual localization is about dreaming. We call this dreaming car, and the question is, can physics still help? So I'm an engineer at heart, and I love deep learning and what's been able to do and transform, especially some of the work that my group has done and the collaborations that I have and things like that. But as an engineer, I sort of just don't want deep learning sort of recreating physics, for lack of a better word. That's because in the last work, we embedded the physics inside of the forecasting. But this is another task that we actually worked on. And the idea here is just like you have the example I gave before, where you'd be driving down the road and you have some missed detections, right? So this is what the image looks like, and this is actually what it looks like in bird's eye view. So there's a whole host of detections that you missed because it's a really tight area and the detector was okay, but not really that great and things like that. But as you drive up to this area, as you drive further up into this area, you'll recognize and you'll start to detect these things. And you're like, oh, well, I missed that detection. So what we did is we would log each of those things, and we would then smooth back. We'd use our physics-based model. We would smooth back and auto label those green boxes as actual cars. So we use our trajectory and we use our estimator effectively running in reverse to auto label these and retrain it. And so basically the idea is you kind of collect data during the day and then at night you retrain. So that's why we call it dreaming car. And if you actually do that, you can see there's just a really big jump in performance over time and things like that. So it's a good way of sort of using physics to your advantage to try to improve the detection task in deep learning. Okay, so now what I'm going to do, so I spent a little bit of time on that. I want to switch gears to the last part of this, or sort of second half of this talk, and talk about uncertainties in deep learning. So you may have seen this if you've studied anything in terms of deep learning. The middle one here is an example I already gave about the Tesla one. There's an example over here where they actually put salt lines around cars, and then the car couldn't move and things like that. This is the one here that I think is a little scary, and that is that if you take a stop sign, you would just put a couple pieces of tape on it. Some detectors think it's a 45-mile-an-hour speed limit. So obviously that is not a very good thing to do. And so it makes these mistakes. I showed some examples before of sort of, I only get partial boxes. Those aren't really bad mistakes. This is a really bad mistake, right? And so then the question is, well, how can you capture those errors? Because many times these networks, they're just making predictions, right? And you have no sense of whether there's an error or not. You might have an average sense because you've been staring at it for a while and things like that, but you really need to have a sense of how many errors it's going to make, and that could change based on the environment, right? If we're driving on a 4-lane highway, all the cars are driving in the same way. There's no pedestrians, so maybe it doesn't make many mistakes. But then all of a sudden, I'm driving on campus at Cornell, and I have hundreds of students around me, and it's just making a host of mistakes. So the environment is also very important. Nighttime versus not nighttime, and so there's a lot of dependencies that go into this. So just to give you a little bit of a background, we're particularly interested in trying to represent this as trying to represent the combination of the detection. So this is the image coming in. So this is the query going into deep learning. This is the data set that's actually learned, and this is sort of the output detection. And then people will just basically put that into an estimator. But again, as an estimator, you really want to know an estimate of the errors that's coming from this z hat, and many times you don't. So this is sort of the most common pathway of sort of integrating these. Sometimes these days these blocks are being combined, so you're actually doing detection and tracking in one network, or all the way from pixels to driving. There's even groups that actually do that. But if you sort of do it in a modular way, you can kind of do it like this. Okay, so I think the ideal way though is a little bit different, and that's you have this transition here where instead of doing z hat, I'm basically producing a likelihood model of what that z would be and the z hat. So it's sort of an uncertainty around z hat as well as the actual detection itself, right? And so then if you do something like that, then I think of all this purple right here I call this sort of a meta sensor. You're combining the pixels coming from, let's say, an image with the deep learning network, and then you're producing a sensor measurement where you also have the uncertainty. So it's really, from my perspective, my group, many times lives in this right-hand block, which is perception and estimation. We have models of what that uncertainty would be, and then we actually get the measurements. So GPS will get, either a 3D position, or we'll get range measurements and put them in a closed loop, a tracking estimator. But for all of those, we actually have some type of uncertainty based on gobs and gobs of data that have been collected in the past, right? So, then our goal is always the same thing, which is to find a probability distribution of whatever object we're looking for. So those are the tasks that I mentioned on one of the first slides, given the data that's actually coming in. Okay, so the key question then is, how do we form this bottom thing here? How do we form a likelihood model of that measurement? Okay, so this is a little bit about some past work. One approach is called ensembling, which works surprisingly well. So basically the idea here is that I have the same data set, and then I train different networks on that same data set. And or I can have the same network and I have 3 different data sets. So I could, in our work, you could do, one of the data sets could be nighttime, one could be snowy conditions, and those types of things, right? So you train each of these things, you get a prediction for each of them, and you basically just create a sample mean and sample variance. So again, I think there's been a number of papers that work on this. If you actually look at a lot of car companies, I know Tesla was doing this at the very beginning. It works surprisingly well. And really what you're doing there is that any one of these networks, you might just be locked into a local minima. But if you have the different ones, you start to get some shape of what that uncertainty would be. You kind of need 5 at least to kind of capture that uncertainty, sort of the sigma squared. But for the most part, that works. I think they have an idea of, it's basically sample-based approaches. So we have an idea of why it works and those types of things, but it's a bit heuristic. It's still dependent on what these data sets look like. So there's no set way of either picking the data sets or the architectures or those types of things. So that's one approach. A second approach would be post-processing. The idea here is that, again, you have 3 different images, let's say, of 3 different cars. You get 3 different predictions. You have the truth measure, and then what you do is you compare the truth measure to your actual prediction, and you create an error. Okay, and so the error here, this is the outputs are in blue, and this is your sort of probability or the confidence level, sort of what's coming out of your network, and then the truth is basically all along this diagonal. And so basically, if it's properly calibrated, which basically means that if I'm guessing that I'm 50% right, then I should 50% of the time get that correctly. If I'm guessing it's 90%, it should be up in here, and so on. So if you have a gap here, that means your confidence is not really matching your prediction in terms of the average probability that you have to your bins. So what you can do then is you can actually learn a mapping then between these outputs here and the actual truth values. Typically, that's a fairly simple softmax. You actually have some calibrated data, which is sort of the green and the pink here. It's sort of the predictions and the truth measures. And then you add that on, and all of a sudden, then you have sort of a confidence level and things like that. So that works okay. It's pretty limited to a certain set of tasks, but what we have found is that it seems to be pretty sensitive to the different data sets and those types of things. And so a final one would be just to replace all of the neurons that you have with basically random variables. And if you do that, that's called Bayesian neural networks. And if you do that, you start to get probability distributions. And so if you haven't seen these before, this is basically trying to find the probability of Z given my query and my data sets. And you can break that down into these weights. And these weights then are the internal weights, but this is a random variable. W is a random variable now rather than simply a deterministic variable. And so there's a very heuristic, there's a heuristic approach that actually has been shown to approximate this. This is called the dropout method. And what you do is you basically drop a layer in your prediction. So I basically say, this network is exactly the same. I send my query image through here and I drop this layer and I get a prediction. I drop the middle layer and I get the prediction, the last layer and get the prediction. And then I do the sample mean and sample variance again. And you can do this randomly. You can do this, especially if you have many, many, many layers. So you can do like 30 or 50 of these. And so the numbers here are much bigger. And actually, again, this works surprisingly well for a sort of subset of the tasks and things like that, right? Typically, if you go all the way here to the left, there's just not enough data to kind of train these variables. It just seems to be very sensitive, even though it's already over parameterized with the neural networks. It still becomes, potentially a problem and things like that, right? So there's still some challenges that actually go into that. Okay, so there's the Bayesian neural networks. So I'm going to go on to some of the work that we've been kind of doing, and this is the case study, the visual localization. So I've kind of already explained this, but I'll explain it to a little bit more in detail, especially in the context of the Ithaca 365 data set. So the idea here is that let's say we drove our 15-kilometer route 9 times. So we have 9 prior traversals, and these now, for each database, I have an image and a geolocation XY pair. Okay, and the XY is coming from our high precision GPS. And then we have our images. Okay, and so we could have nighttime or sunny times. It depends on what it is. So now I'm driving. This is an image of downtown. I'm driving. And I say, okay, well, now I have my image. I want to say, what is the closest image or the top 10 or whatever I want to do from my data set? So remember, each data set has 17,000 images times 9. So that gives you how many data sets you actually have in there. And I want to pick out the best one out of there. So if you have an image like this actually is looking at a movie theater and those types of things, maybe that's actually not too bad. But if you get out into some other areas where it actually looks fairly similar, like a highway scene, then it's a little bit harder. Okay, so that's what's happening in here. We're now driving this area, and we're actually trying to match those. And we match it to our top one, and then we pick our position. And that's what our position is, right? So we're using this now as an example. I think visual localization is a good task, but it's really good because of the data sets we have to evaluate different ways of doing uncertainty modeling. Okay, so this is our network that we use for visual localization. I don't want to spend too much time on it. Basically, at the time we sort of put this together, you can see this is a little bit older in terms of some of the things we were doing, but basically we picked out some features, which actually happening in here. And then we did some matching of those features. So think of this as sort of a coarse step and then a fine step to figure out sort of which one those work on. All right. And we subsequently have looked at this a little bit in terms of some of the more modern networks, transformer networks and with attention and those types of things. But this is pretty good for just sort of evaluating different approaches to uncertainty modeling. So the first thing we did is we just evaluated the straight up errors, because remember, we have the truth GPS for each one of the images and things like that. So under sunny conditions, you can kind of look at this. This actually looks pretty Gaussian, right? So I have a lot of my errors sort of sitting in the center here. It's actually, this is the 95% ellipsoid, which is typically 2 sigma, and the 2 sigma here is roughly like plus or minus 1 meter. So it's really, really not too bad. You have these outliers that, kind of go out 2, 3, 4 meters. But you have outliers already in GPS and those types of things. So that's really not too bad. If I go over here to the right, this is the snowy conditions. You can see there start to be a shape now to the errors, which is kind of interesting. And it's a little bit bigger. So you see the 2 sigmas out to about plus or minus 2 meters, but I have a little bit more errors that are outliers, and it doesn't look like an ellipsoid as much anymore, right? But it's still concentrated in the center, so that's actually good. But if I look at the nighttime conditions, and this is just wacky. So basically what's happening here is that, it's plus or minus 10 meters, you see these forays that are actually going in here and things like that. This is basically locking on to a feature and then never, and always thinking it's, or an image in your database and always thinking it's the same one. And it isn't. You're incorrect, right? And so it makes basically these deterministic long-term errors that sort of just, go off on its own and things like that. So you can imagine if you're trying to localize using this information, it's really, really hard to kind of deal with. So we started analyzing this a little bit more. We looked at these data points, the feature points. These are the features that are actually coming out. And it was kind of interesting. The sunny conditions, we sort of have a minimum of 200 features in the image. That's what this is showing right in here. This is basically the error as a function of the number of features. That's what each of these plots are. And so you see, for the sunny conditions, we pretty much, except for these three in here, we have almost 200 features in each image, right? And most of the errors are sitting down here again, sort of in the, low, almost like under 1 meter and things like that, right? The nighttime conditions are exactly the opposite, right? I only have very, very few features going on. I have high errors that are going on and things like that. And snowy conditions are kind of a mix. In terms of some of these low errors, if I lock on, it does a pretty good job, but sometimes I have some low features and some errors that I just can't quite figure out what's going on. So these are just some, if you want to sort of understand a little bit about what's going on, effectively at the nighttime conditions, when you have lights and things like that, you just have fewer matches and just poor illumination. It locks on to, let's say, images of the car and it's moving and things like that. It can't really, far away, can't tell the difference between, some of the lights that are actually occurring and those types of things, right? So that's the kind of mistakes it makes. Also, this is a picture of downtown Ithaca. And on our driving, and we didn't realize this till afterwards, but there's a brick street in downtown Ithaca that we drive over, and so you see all the features that are actually pulled out here, all sitting right in front of the car. So even though it's sunny conditions, we had some outliers in here that's actually occurring as well. Because again, if like 80% of your features are sitting down here in brick, and I'm sitting here, but I move ahead, even just, 5 meters, I can't tell the difference between this point and this point. It's just, maybe from the outlier points in here, you can actually do that. But it was interesting. It was just being swamped by these features coming from the brick. All right, so I'm going back to this again. Our goal really was to develop this bottom likelihood model. That's really what we actually wanted to do. So I'm going to show a bunch of different images here of the error covariance, and we use a test statistic, okay? And there's two things that are going on in here. So again, we're trying to estimate this. Think of this as just the covariance. That's what we're trying to estimate R. We have the ground truth Z, and then the Z ground truth, and then this is Z prediction. So we create this test statistic, which if this was Gaussian, then this test statistic would be a chi-squared variable. And you have different kinds of errors, okay? The nice part about this is it's always positive, right? So the common error is if Z minus Z ground truth is really large, those basically the lambda is really, really high. And then, however, there's some errors where I actually just pick a really, really big covariance. It's just too big. And it's sort of like saying, okay, here's your prediction, but it's, plus or minus 500 meters. And then, so it doesn't really give you any information. So that, in that case, you have some errors, but it's actually at the low end of things. So, so I'm going to actually show basically how this works. So as a baseline, what we did is we basically said, okay, we're just going to take the data sets, some separate data sets, and find a constant covariance, and let's see how it works. So this is the first one. This is the baseline in terms of constant covariance. So again, this is our errors that we're looking at over here. Each of these plots, you're going to see a few of these as we go through here. Each of these plots on the bottom, this is us driving the 15-kilometer route. So starting basically on campus, this is us driving downtown in the 2,000 range. If we get to the 5, 6, 7,000, this is out on the highway. 8,000 is basically, we subsampled this, by the way. 8,000 gets us back into suburbia, and then right at the end here, we're based back on campus. So and so you can see sunny, night, and snowy. So if it is Gaussian, and we're not saying it is, but if it is Gaussian, and we put this on a log scale, so again, the orange looks a little bit bigger. That's only because we put it on a log scale. We'd love these to be matched the 5%. So this is sort of capturing the tail. So in the sunny conditions, I got 5.8%, 6.3%. That's pretty good. It's not too bad in terms of estimating that. But if I actually go to the nighttime conditions, you see really big jumps in the errors up in here. So I have really big errors. Okay, and the snowy conditions, everything sort of shifts up in terms of what's actually happening in there. Okay, so really, these big errors are problematic, but even over here on the right hand side is creating some potential problems. And so these, so then the question is, what's happening? That's actually when we were driving on the highway. And driving on the highway is just really hard to tell the difference between, one point on the highway and another point on the highway. So this is, oops, do I have this? I think I just have images. So if I look at, this location and this location, I can't really see much of the difference. It looks like a highway. If I'm entering the highway, maybe I understand it. If I see this sign, maybe I can understand that. But sort of in between, it's really, really hard to see what the difference is and things like that. You just don't have a lot of key points. It kind of all looks the same. And so that's the kind of error that it actually makes. Okay, so one solution is actually just do a data-driven covariance. And so based on the key points, so basically however many key points I have, I'm gonna look up all the images that that have previously been found in our database. And then I'm gonna basically do an average of what the covariance is in. And so I basically bin these things up and I create a covariance based on that. So the covariance changes at every time step, and it's basically a function of the it's a function of the number of key points in the past data sets we've been doing. So if you do that, we call this adaptive covariance because it changes at every time step. And so if I look at this, again, these are the same images and things like that. There's a few things you want to see. The first thing you want to see is that all of those large errors are gone, which is really great, but it's actually driven them down to be really low. So effectively what happens is there's so few features when you're driving out on the highway that it creates just a huge covariance, which makes lambda really, really small. So effectively, it does a nice job of capturing the outlier errors and adapting the covariance, but it's kind of overcompensating is what it's doing. And it's doing that across the board. So this is now 11% and it was like 5, and the same thing over here, it's a little bit larger. So that's a little bit of it's a little bit better, but still, potentially problematic. Not as bad as the first one and things like that. And so this is just an example of what the errors look like. This is us driving. This is the sigma when you're actually driving out on the highway, and basically it's just much, much higher as you go out all the way outside of there. Okay, in terms of the nighttime condition, you can see it goes all the way out to 120 or even higher. Okay, yeah, the scales of these are very, very different. So they look similar, but they're very different. So this sigma is 1.2. This sigma in the nighttime is about 80, and then this is about 1.8. Okay. So another solution, this is some recent work from ICRA 2025 that my student Shuman worked on, is we wanted to add in semantics. So basically some semantics of where the road is, the sidewalks, and rather than just using features, let's add the semantics in and see how it works. And these are slightly different figures. We really wanted to look again at the because we figured it was already going to be non-Gaussian, and so we wanted to look at the tails of the distribution. And so the baseline approach, which is our adaptive covariance, basically looks at the top right in here, and you can see it still has some problems with the tails of the distribution. But if you add semantics in, you still have a couple outliers, but not really too many. And the same thing in the snowy conditions. So it really does a nice job on these harder conditions, which is night and snowy, if we add in the semantics. And then some current work, we're actually using some transformers with attention, and attention allows you to focus on what part of the image is really important to what you're doing. It also has embedded inside of it a way of sampling that allows you to get to give you some uncertainty and things like that. And this is actually doing a really pretty nice job. So this is still a little bit high, but for the most part, we just kind of trained it up, and it's actually working really pretty well. So that's pretty nice. So that's some current work. Let's see, about 1243. Okay, so the final thing is that's all based on just quantifying the uncertainty. Now what we want to do is put it into a filter to figure out what it is. Because, if you have like an IMU or something like that, you can actually start to reject some of these uncertainties. And that's what this block diagram shows. So this is now a typical block diagram where you have the sensors, you have a measurement in the uncertainty model. You might do some measurement integrity where you actually do a chi-squared hypothesis test. You gate the sensors, and so any outlier errors you can typically pick up with that. This is your measurement update, and this is your prediction step. And so we basically compared this to a traditional based approach in our visual localization to figure out what's happening. And this is some of the analysis of what we're doing. This is the average error of the data itself. So you kind of, if you think about those sort of scatter plots that I had earlier, where the nighttime was showing a shape, but the sunny condition it looked like a Gaussian. This is basically the average of those plots, and so this is under a meter error here, 8.7 meters and 1.4. If you then put it into the with a basically a time average, not an IMU, but basically a time average prediction step, it does a pretty good job. It sort of takes this error, drops this down to 0.76. So each of these actually come down, a little bit. It goes from, the baseline really drops here from 0.76 to 0.5, 8 down to 3, and 1.3 down to 0.8. But these are basically 1 sigma, 2 sigma, and 3 sigma. So you'd like these, especially the middle one, to be 95%. And that starts to show you, are we capturing the tails very well? And again, this sort of overcompensates, but still does a pretty good job in terms of what it's doing. Okay, so a couple of just images of how this is some of the hard examples that we're doing. This is us just sort of the query image. This is the baseline as we're driving on snowy conditions. And what you're looking for here is the fact that the green is the ground truth, is basically goes outside the uncertainty. So basically the uncertainty here, it locks on because it can actually see the sign. Let me come back here, I think right at the beginning. If I start this, yeah, so it's sort of not in there, but as soon as the sign comes closer, so basically this is error, getting closer, and then eventually, because the sign is close, does a pretty good job. But this uncertainty over here is much, much bigger, and that's basically because we're adapting the covariance to kind of show that it's actually, it's a harder estimator, it's a harder detection, and you're going to make more errors. Okay, we did everything, the things like corrupting the images, making them look snowy in nighttime conditions, and adding noise and blur and those types of things, and actually picked up all of those. This actually did a very, very nice job, but these are kind of uniform in terms of the errors. But it had really no problems working with these kinds of things. It was sort of the harder conditions that I showed in the last video that sometimes a little bit more of a challenging. Okay, in the last, I know I'm a little bit over time. I only have a couple of slides left to kind of talk a little bit about this. I have visited Hanoi, Vietnam a couple of times, and in my last trip there in October 2022, I actually brought some sensors with me, some LiDAR, vision, and GPS, and actually took some videos. So this is us taking a video just to give you an idea of the scene here. And you can see just tons and tons and tons of scooters, a very high dense environment. Turns out that there happens to be traffic lights, but many times there are no traffic lights. It's basically just kind of a free-for-all, but there are behaviors that people sort of learn based on that. So there's some successes, and so these are basically just instance segmentation, just running it through a network. And if you look at these, you can see it actually did a pretty good job on that orange one, pretty good job this one on this one here. So that does a pretty good job. But this one, eventually what happens is I sort of miss this one, it goes behind it, and then I can't see it anymore. And that one goes behind there and I can't see it anymore. So once, anything that's close and included, I sort of pick up, but once it gets more than a couple meters away, it becomes problematic. So what we're working on are problems such as that. So in summary, I think the deep learning has really revolutionized the processing of these large amounts of data using all of the that you get from high density pixels and LiDAR and things like that. But it makes unpredictable mistakes. And it's even harder when you look in some of these other environments. And so one is the snowy conditions, which is what I have in here, and then this is another video actually from Vietnam. And I think these are the two conditions in particular we're interested in doing. Like the snowy condition, this is some data that we actually took. This is actually coming on to campus, Cornell's campus from North Campus. Some people during a snowstorm, some people coming out and pushing a car. You can see all the pedestrians that are happening in here. It's pretty wild what they're actually doing. And then, students, this is a car U-turning as we go through here. Actually, let me pause this right in here. And these are some students that are just, walking across the street and then stopping in the middle of the road, right? So you can't even see the road, but they're just stopping, right? And at this time, my student Carlos was driving the car, and basically all classes were canceled. So the students are probably trying to figure out whether I'm going back to the dorm room. So that's why they're like, okay, yeah, I'm going back to bed. And then the one on the bottom here, again, this is just some videos from Hanoi. I think this is just wild here, this intersection, where cars, and it's just a free-for-all, right? I mean, there's no lights here, and everybody's just kind of crossing, and eventually you're going to actually see some pedestrians that are crossing that just look really, really scared as they're kind of doing this. Yeah, that's what they're doing right in here. So they're just kind of walking through here, and I had to cross a couple roads like that when I was there. Somebody just held my hand the whole time, because they're just like, if you stop, then you are unpredictable, and they're going to come out and kind of say, okay, this is not good. And then this is one of my favorites. They're just selling balloons right in the middle of the intersection, which is pretty wild. Anyway, so I think these are some of our challenging scenarios that we're still trying to looking at. We're still trying to capture these things. The deep learning and the approaches are just changing by the day. And so what we typically do is monitor some of the networks and what they're doing, and then figure out, okay, how can we adapt those to give us the uncertainties that we need to build a belief about the environment and things like that. And I think that is it. Yep, those are just the references in part of that. Okay, that's it. So I'll open it up to questions now.
Thank you very much, Professor. I have one question. Your visual-based odometry, your visual-based localization method, could you elaborate, how does it compare with state-of-the-art, how, for example, Tesla or Waymo localizes their cars?
Yeah, I think most groups use GPS now. They do GPS with a pretty good IMU. It's not a high precision IMU. In the competitions and other things that we've done, we have a pretty good IMU. But there's also services now. So for instance, GPS now, you can do corrections and things like that, but there's also services you can buy into. So for instance, we have an antenna on top of our roof that measures GPS errors. That's probably one way to think of it, or at least the probabilistic errors. And then we subscribe to that service and we subtract those errors off. So I think that works really pretty well. But then if you get into my family lives in the middle of nowhere, Pennsylvania, or they used to live in the middle of nowhere, Pennsylvania, right? And GPS cuts in and out, right? And certainly the service cuts in and out, which is always a little bit hard. And but then if you're driving in Manhattan, for instance, you're going to lose those types of things. So I think there's times for using visual localization as a task, and I think as a backup, I guess what it is. So there's actually been quite a bit of research on these kinds of things, right? But I think for the most part, most cars right now will try to use GPS to kind of do everything they actually need to do. They may use images and those types of things to figure out where they are on the road, and then use GPS to kind of navigate, right, more than anything. So, but the final thing I'll say is that I think I want the takeaway here. I don't want the takeaway here to be, hey, Campbell's group really is trying to do great things with visual localization. We actually just use it as a really, really good example to try to do uncertainty quantification in different types of deep learning networks. And it was really good for us to study it because we have these multiple paths or multiple data sets and things like that. So we can compare, how does it work at nighttime versus not nighttime and those types of things. It's hard to do that with detections and those types of things because the scene is really changing. Looking at a small car at night is different than looking at a van during the day. And so, those kinds of things.
So I recall in the night, your results showed that the camera-based localization is not performing so well. Would you say that then the LiDAR needs to come in and help?
Yeah, the LiDAR would help much better at night. Yep, the LiDAR would definitely help at night. I mean, LiDAR doesn't have the range really of some of the images and things like that. It kind of depends on what kind of LiDAR you put on. And then there's some cars like Teslas don't even put a LiDAR on, right? So I think LiDAR, I'm a fan of LiDAR. I'm going to just say it that way. I mean, I think it's really good for safety. I think it's really good to use and things like that. It has its own challenges. It's kind of expensive. And it doesn't give any context, right? So for instance, if I have the deep networks are good at this, but if I have something that looks like a wall, I can't tell if it's a wall or something else, right? But in an image, I have the context of the scene. I have semantics, right? Of the scene, and so the images are a little bit better. So in reality, the best thing you can do is combine them. It really is. They either combine them, do detections on both, or basically combine them in a data set such that I have 3D points, but I also have the context of the scene from the image itself. And so in my mind, that's the ideal.
Perfect. Thank you very much. I do not see any questions on the YouTube, so we can wait or conclude here, as whatever you like.
I think we can probably conclude if people have any questions. I think they feel free to kind of reach out to me. I think it's kind of been fun. The things that we've been working on. I think it's been pretty challenging, and it's evolving all the time, especially with all the things we're doing with deep learning and things like that. So, but certainly, if anybody has any questions or comments or wants to see a paper or something like that, feel free to reach out to me.
Thank you very much, Professor, for this excellent seminar. Thank you very much.
Okay, thanks, Panos. Take care.
Thank you.